Hello, everyone, and welcome back. In the previous lecture, we defined an indefinite integral, which captures the set of all possible antiderivatives of a function. We also introduced the method of substitution, which allows us to directly calculate these antiderivatives by undoing the chain rule. In this brief video, we're going to talk about how we can use the substitution method to evaluate definite integrals. So let's go ahead and get started. Now, one method by which you can evaluate integrals for which you can apply the substitution method is to first just use the substitution method for indefinite integrals and find the antiderivative and eventually find this full antiderivative as a function of x. So go through all of the examples that we did in the previous lecture, go through all of that work, and then plug in the bounds, right? Applying the fundamental theorem of calculus, part 2. But there's a simpler way to do this. And this is known as the substitution method for definite integrals. So for definite integrals, and it can save us quite a bit of work. Essentially, what it allows us to do is by substituting the variable x in terms of u, then we can also substitute the bounds in terms of u. So it says that if g prime is continuous, alternatively, if g is a differentiable function on the interval AB, and f is continuous, on the range of g of x, and we're going to call that u, remember from the substitution method. And we need this f to be continuous on the range of g, because remember, we're dealing with function compositions here. So this says that then the definite integral from a to b of an integral of the form where we can use the substitution rule, so f of g of x times g prime of x, well, then this thing is the same. Remember, from indefinite integrals, this becomes f of u du, but then the bounds just become g of a and g of b. So that is the same as u at the value a and u at the value b. Okay, so why is this the case? Let's go ahead and prove this, and things might become slightly more clear. Well, if we use capital F, so to denote the antiderivative of little f, so let f be such that capital F prime is equal to little f, then we get, so the left-hand side here, this can be written as capital F at g of x going from a to b, right? This just comes from the fact that capital F is an antiderivative of little f, and I'm just undoing the chain rule here. And by definition, this is f at g of b minus capital F at g of a. Again, all I'm doing is evaluating those endpoints. But this is the same as saying f at u, where u runs from g of a to g of b, right? So I just hid the g function inside of u here, right? And this, from the fundamental theorem of calculus, is the same as an integral running from g of a to g of b of little f of u du. But now what you can see here is I've got the left side and I've got the right side. And by this string of equalities, these things are exactly the same. So this may not seem like much, right? It might be hard to appreciate how great this is, but this essentially saves us a ton of work, because this means that we don't have to calculate an indefinite integral, find an antiderivative, and then put everything back in terms of x, and then apply the fundamental theorem of calculus. It says that we can do it all on the fly. So while you're doing the substitution, you can just substitute the bounds as well. And therefore, you can just use the fundamental theorem of calculus to evaluate these things. So it'll save you a significant number of steps. So let me give you an example. So example 1. Now, let's suppose we're asked to evaluate the integral from -1 to 1 of 3x squared, and then the square root of x cubed plus 1. Okay, so the substitution method can be applied here by substituting for u is equal to x cubed plus 1. Now, why is it that I see that? Because I can see this x cubed plus 1, when it becomes differentiated, it turns exactly into 3x squared. So what this tells me is that this integral, if I put an equality underneath it, if I let u, sorry, that's more of a y than a u, if I let u equal to x cubed plus 1, then from what we talked about in the previous lecture, I get du is 3x squared dx. So I'm not going to put the bounds on this thing yet, but the 3x squared and the dx all make up du, and I get the square root of u du. And now what I can do is I can replace those bounds. So I have, from this substitution for definite integrals, it tells me that I just need to evaluate u, or g of x, same thing, at the upper and lower bounds. So the lower bound is x is equal to -1. So then I get u of -1 is equal to -1 cubed plus 1, which is equal to 0. And when x is equal to the upper bound at 1, I get u of +1, which is 1 cubed plus 1, which is 2. So that tells me that my bounds now become 0 to 2. So this is becoming a little bit of a mess. Let me rewrite this nicely over here a little bit. So I want this thing becomes the integral from 0 to 2, square root of u du. But now this is a very easy integral to evaluate. This is equal to 2/3 u to the 3/2 running from 0 to 2, which is equal to 2/3 2 to the 3/2 minus 0 to the 3/2, which I'm going to squeeze this in just because I'm running out of a little bit of space here, but after some manipulations, this becomes 4 times the square root of 2/3. But look at how significantly simpler that is, right? I didn't have to go back and put things in terms of x. I could evaluate the bounds in terms of u. So this saved a significant amount of space, and it saved a significant amount of my mental space, right? I didn't have to keep track of too much. Things were relatively simple by just changing the bounds in this case as well. Okay, let's look at another example. Sorry, example 2, right? I'm getting ahead of myself. Okay, let's look at the integral from pi/4 to pi/2. You see the pi's in there? We know it's going to be trigonometric, right? cotangent of theta times cosecant squared of theta d theta. Again, don't be intimidated by that theta, right? Theta's not doing much. It's just the independent variable. You can call it x if it makes you more comfortable. So the question is, what is it that we want to substitute for? Well, this might take a little bit of refreshing, but the derivative of cotangent is exactly negative cosecant squared. So I'm going to let u equal to the cotangent of theta. And this tells me that du is equal to minus cosecant of theta squared d theta. Now I don't have a minus, but I can rearrange for the things that I do have. I do have a cosecant squared. I do have a d theta. So this tells me minus du is equal to cosecant squared theta d theta. Okay, I'll come back to the bounds in a moment, but let's write down what we have so far. The cosecant squared and the d theta all become du. Minus du. Let's put the minus out front. The cotangent becomes a u. So I've just got u du here. And so the question is, what do the bounds become? Well, when theta is equal to pi over 4, then u of pi over 4 is given by cotangent of pi over 4, which is just equal to 1. And when theta is equal to pi over 2, I get u is equal to pi over 2, being the upper bound now. And this is equal to cotangent of pi over 2, which is just equal to 0. So this tells me that the bounds now become 1 up to 0. Now there's a few things that you can do here, right? You can do the straight evaluation of this thing. But I have this weird thing. I don't like having numbers out of order, right? So this integral is kind of going backwards, right? So I can apply, I believe it was property 1 from definite integrals, to get rid of that minus sign by flipping the order of integration. This is the same as going from 0 to 1 u du, which is 1/2 u squared running from 0 to 1, which gives me 1/2 1 squared minus 0 squared, which just gives me the definite integral is equal to 1/2. So wasn't that nice? It was nice and compact, right? We got to change the bounds all in the same step as we were changing the variables. Okay, so let's look at one more example. Example 3. So in this case, we're asked to integrate from minus pi over 4 to 4. So again, pi showed up, definitely going to be a trigonometric problem. Tan of x dx. Okay, so immediately it doesn't really look like there's two functions in there, right? So it looks like it's going to be a little difficult to do our substitution. But let's remind ourselves that tangent is equal to sine over cosine. So let's write this. At least then we've got two functions to work with. So I get sine of x divided by cosine of x dx. And so I believe in the last lecture, I asked people to try this out on their own. I hope they did, but if not, I'm going to ruin a bit of the surprise for all of us. So I'm going to substitute for cosine of x. And so then I get du is equal to minus sine of x dx. Again, I've got the sine of x, I've got the dx. I just need to put the minus on the other side of this thing. And then the next thing that we need to do is we need to evaluate some bounds. So when x is equal to minus pi over 4. This gives me that u of minus pi over 4 is equal to it's equal to cosine of minus pi over 4, which is equal to square root of 2 divided by 2. Then, when x is equal to positive pi over 4, this gives me u of pi over 4, which is the same as saying cos of pi over 4, which again gives me the square root of 2 over 2. So let's put in all the information and then let's talk about it. So I get an integral running from the square root of 2 over 2 to the square root of 2 over 2. And then I have the sine dx becomes du. The cosine becomes u. And so take a look at that. See what happened, right? Well, in this case, the upper and lower limits of the integration are exactly the same. So I believe it was property 2 of our definite integrals, which told us that this thing is 0, right? Remember, if we think of these things as area under the curves, well, there's no width, right? So of course this thing has value 0. So that made our life so much easier, right? If you were to do this without substitution, which I'm not 100% sure one could do, we see that things would be much more complicated. But because the bounds collapse down into the same values, things are pretty nice, right? We know that this integral is 0, and this took me, what, 2 steps, 3 steps to be able to do. Okay, so that's all that I want to say for this. Gave us some nice examples. It told us how we can use the substitution method for definite integrals.